Hi, everyone. I'm Marshall Trout. I'm an electrical engineering graduate student in Dr. Jacob George's neurorobotics lab. And today I'll be presenting and talking to you about reanimating a hand through non-invasive electrical stimulation for stroke rehab. So a bit about why we're interested in reanimating a hand. Stroke is the leading cause of long-term disability in the world, in part due to hemiparesis, which is the partial paralysis of one side of the body. In the upper limb, hemiparesis manifests as either a flaccid or a spastic hand. In a flaccid hand, the hand is characterized by the muscles lacking tone and the hand being overly limp or relaxed and being unable to contract. While with a spastic hand, the hand is overly flexed and curled into a fist. So here we have our flaccid hand and our example spastic hand. In both cases, really the main form of long-term treatment is physical rehabilitation. It's really the only way to restore long-term functionality. One form of demonstrated physical rehabilitation is mirror therapy. And in mirror therapy, a patient places their paretic hand behind a mirror and their healthy hand in front of the mirror. And then they imagine moving their two hands in sync. And while the paretic hand isn't necessarily doing what the healthy or unaffected hand is, this has been demonstrated to increase hand function in stroke populations just through the visual feedback paired with them imagining moving their hand. We're investigating improving this through reanimation, so that rather than having the patient imagine moving their hand, they would be moving their healthy or unaffected hand, and then through electrical stimulation, we would be moving their paretic hand. We believe there might be gains in terms of the rehabilitative aspects, because not just visual feedback is given to the patient, they'll also be receiving proprioceptive feedback and cutaneous feedback from the affected limb. And so hopefully the idea is that this could quicken the rehabilitation process. So to this end, we're developing a system that can match the grip force between two hands using non-invasive stimulation. So a bit about how non-invasive stimulation works. Animating hand movements through non-invasive stimulation operates by passing electrical stimulation through either the muscle belly or the nerve trunk. In this work, we're going to be focusing on stimulation applied to the nerve trunk. While the muscle belly is kind of the classic stimulation site, the nerve trunk has been shown to have some benefits, specifically in a slower fatigue rate. And then so once you apply electrical stimulus to the nerve trunk, the stimulus moves down the motor fibers, or the motor fibers activates the muscles and evokes grasp that can be measured using a load cell. So to suit our needs in this project, we've developed a custom designed stimulator to supply non-invasive stimulation. We designed this PCB such that 3 channels can be stacked on top of a microcontroller. And the stimulation circuitry itself is based on a Hallen bidirectional current source, so it can supply current controlled biphasic waveforms. The current amplitude, pulse frequency, and pulse width can all be set online, so you can vary all these parameters during your work. And with this system, we were able to supply waveforms with a compliance voltage up to plus minus 200 volts, which is necessary for getting through the skin, with a minimum pulse width of 50 microseconds and a resolution of 10 microseconds. And also one benefit to this system is the cost for a single channel is approximately $90 to $100, which is much less than commercially available systems. So with the stimulator, we have previously demonstrated that stimulation applied to the nerve trunk can evoke a variety of independent digit motions, depending on the location of the applied stimulus. So here are some examples with flexion of the index finger, flexion of the pinky, and then flexion of the ring finger. And we can all see that these are fairly independent motions. We have since, we've further developed this system to control our custom stimulator using signals such as grip forces. In this presentation, we'll be focusing on the controller that we settled on to close the loop between the grip force and stimulation current for our improved mirror therapy system. So a bit of a roadmap of what we'll be talking about. We're first going to start with the discussing the controller design we used, and then we're going to follow up with a validation of the control scheme. So in this work, we decided to go with a feed-forward feedback controller to supply current to match the grip forces between the paretic and healthy hand in real time. It consists of a feed-forward portion that calculates a current based off the unaffected hand's grip force using just a kind of basic model that we'll talk about here in a bit, and a feedback portion that calculates the current based on the difference in forces between the unaffected and the paretic hand. So now we're going to focus about each part, the two parts of this controller, starting with the feedback option or portion. So feedback-based control is definitely kind of the simplest and the most classic control approach for this setup. And in it, you have the difference between the paretic and healthy hand is use a control signal to drive a PID or other kind of basic control scheme. However, one of the issues with this is since each patient is unique, the relationship between the current and the grip force is unknown. So the controller would need to be tuned in every case. This is undesirable because tuning a controller, you would need a trained technician as well as a fair amount of the patient time to fit the controller to each individual patient. And so to address this, we added this feed forward portion of the controller to decrease the time required to tune the system for each patient. So rather than tune the controller to each patient, we generate a model from experimental data. So once we have a proper stimulation site has been selected, the patient steps through a range of currents at their own pace, and we collect their grip force data. And this is able to kind of capture the relationship between the patient's grip force and current and give us information about where the minimum threshold and the maximum threshold are. We're also able to fit just a simple linear model to this data. And this kind of provides us with a basic lookup table of how much current to supply to evoke a certain grip force. However, we can see that there's noise in this data and error in the model. And this is what the feedback portion of the controller is for, is to correct for any inaccuracies in the model. So now that we've covered the controller's design, we will now discuss kind of how we validated it. So we validated this control scheme just using a single healthy individual who relaxed one hand in order to mimic a flaccid paretic hand. Stimulation site was chosen to evoke a full palmar grasp, so they're just opening and closing their hand. So here are some of the results, and we can see that with the blue curve is the stimulation applied to the relaxed hand. And then in black, we can see the controlling hand, and in red, we can see the relaxed hand. And you're able to, just from visual inspection, see that the signals follow each other fairly well in real time. And so when we compare that to just kind of a standard basic feedback controller with a similar tuning, we can see that the feed-forward feedback control scheme has considerably less error over the course of a trial. And so from this presentation, we can see that we now have our improved mirror therapy system for stroke rehab. And the next step will be kind of branching it to stroke patients. And we'll talk about that here in a second. But also more important as well, to our knowledge, this is also the first demonstration of a closed loop stimulation applied to the nerve trunk. Most previous work has been done in the muscle belly, non-invasively, that is. And so with this system, we'll be able to mimic forces between the paretic and healthy hands in therapeutic settings without having trained personnel to tune the controller each time. So you could, in theory, hand the system off to a PM&R specialist, and they should be able to use it themselves without having an engineer help out. And so, as I mentioned that earlier, is our next step in this research will be demonstrating the system with hemiparetic patients. While the current design would work with a flaccid hand, a bidirectional system would need to be developed for a spastic hand to open and close the hand. So stimulation will have to be applied at two different sites to evoke flexion and extension. And in order to address this, we propose an extension of our current system where you would just have two models, one for flexing the hand, one for extending the hand, and then you would still have your feedback portion. And then you would effectively have an electrode selector that shows what stimulation site you went to open or close the hand. And then once we've established the bidirectional control in stroke patients, we plan to take this work even further by expanding the number of stimulation sites using a sleeve of electrodes to evoke a wide variety of independent finger movements in a paretic hand. And so this would kind of create a improved mirror therapy that, rather than just having a simple open-close grip, would allow the patient to practice more dexterous tasks that include like individually moving certain fingers or making specific gestures. I'd just like to thank everyone who's helped me out in this project, everyone in the lab, in particular my PI, Dr. Jacob George. Are there any questions?
That's great. I think I can talk about that.
Yeah.
Marshall, this is really cool. I'm happy to see how this has developed. I've got two questions for you. So the first is your model choice, your kind of simplification. You chose a linear model, which I think is a kind of good first approximation. But a lot of this stuff can be explained oftentimes with sigmoids. And in particular, I noticed in your data that like right about the 6 microamp point, it almost looked like it plateaued if you just didn't use anything from 8 and above. But that kind of keyed out to 4, was it kilograms per something in terms of force? And in the data that you showed, there wasn't anything above 4. So why elect with going with a linear model when that may be a little bit less accurate when a sigmoid fits part of your data best, particularly in the region that you use the most?
Yeah, no, that's definitely a fair question. Part of the variation with patients, so one of the reasons we've gone with a linear model is we've seen that part of it depends upon the participants' willingness to explore a wide range of amplitudes. And so if you have someone who's more hesitant, then what you end up with is they'll start to evoke very small grasp forces, like on the order of like less than a kilogram force. And so you end up with the start of that sigmoid curve, and then you get 2 or 3 data points after that. And so you have this line and then it stops. And so that's why we've gone with the linear models. It just tends to fit those cases.
Understood. Second question. I know in this space, we all love to ignore the problem of fatigue because it just completely destroys everything. But in your cases, how well would this controller still operate if all of a sudden this model, feedforward model that's based on, is just not accurate?
Yeah, no, that's another great point. Hopefully the idea is that the feedback portion, that as the person begins to fatigue, if you had a aggressively tuned enough feedback portion that could just fit a general population with the aid of the feed forward portion of the controller, the feedback portion would be able to correct for some changes in fatigue. Obviously it won't correct for all of it. And
have you ever reached a point where it's just like, this is not doing what it's supposed to be?
I definitely have. Yeah, there's definitely some point where after a handful of minutes of stimulating someone continuously, especially at the higher currents, you can see the muscles fatiguing, and even have had comments of people saying like, oh, I can't really open my hand anymore, or I can't close my hand. So
thank you.
Yeah, no, thank you. Yeah, Tom.
Do you have any strategies to sort of allow yourself to reach higher amplitudes of stimulation, like without causing the patient discomfort? Spread around electrodes or apply anesthetic or anything like that, so you can have more, a little more current?
Yeah, no, that's so all this work so far has been done with healthy participants. And so before we start looking into options receiving that, we're looking at moving that into a stroke population, because it's somewhat unclear to at least our lab what range of currents they're comfortable with, because they do have some amount of sensory loss. So it might be that that's not necessary, but also we're trying to not really push the amount of current someone can take, just because it seems we prefer to create a therapy that people feel really comfortable with, as a lot of people already have hesitations with electrical based therapy in the clinic for an upper limb. At least most people just stick with kind of the classic, like having a physical therapist open their hand, as opposed to having an electrical system open their hand for them. But you're right, yeah. If you were to include multiple electrodes or possibly include just larger electrodes, you'd be able to see an increase in like the comfort threshold. Yeah.
I've got one more.
No, you're good.
Because this one's much more in line with my work that I have, but I know at one point we had talked about, what kind of controllers you could use. And one of the ones that we found a lot of success with, or was relative success with, this model predictive control, where you build up this model kind of beforehand of how the thing is going to perform, which is very similar to this. But then you adapt the model in real time instead of having this sort of feedback PID loop. Did you guys do any sort of exploration onto that end, or did it? What would you see would be like a complication where that wouldn't fit?
Yeah, so I mean, this is definitely the work presented here is a first pass, and moving on to model predictive control is definitely something the lab is looking at as something to provide a higher degree of control.
I think it also might provide some robustness too.
I think it will as well. One issue where I see model predictive control failing is the model to a certain degree is going to depend so much on the arm's position in space. Not that this control scheme would necessarily handle this well either, but it's unclear as to what will especially with nerve trunk stimulation, just like a slight rotation of the shoulder completely changes the nerve's position relative to the electrodes. And so if you have, even with a more robust control method like that, if you have the patient or participant moving around at all, most of these models are going to change drastically and very quickly, just like I said, like a slight rotation of the wrist can completely change the models that we're generating here. So